something. Yeah. So assume. So this will be a page table entry at the inner level. Okay. So this will have some kind of addresses, and this level will create the second level page table, and each second level page table will have third level page tables, right? So, so let me. So assume this is a L1 page table. This is a L0, L012 or L123. How do we call that?
It
So
starts with 2, L2, L1, L0.
Okay, then it tells 2. So this is the initial level 2 page table, and so this has some address, right? So this is a directory which will be pointing to the next level of things. So consider a virtual address. So assume our program uses a virtual addresses from a limit 0 to uh, some hexadecimal number, right? Let's call this uh, 0x ffff, maybe some, assume this is some number which is the maximum need for our addresses, right? Or maybe there could be some addresses in between which are not used. Okay, so for those page addresses, we don't create the next level of page tables. Okay, so there will be this. How do we select? So we put it down. Oh, it's, I'm not sure why this is pasting that here. So let me draw a new line. Yeah. So this is L2, right? So assume there is this page directory, and this is an page table entry pointing to this page at which this page table directory. Okay, these are all directories. So this will be pointing to this page table in the next level, which is will be called here L1, and then this will have multiple page table entries, right? This will have multiple page table entries, and assume this one is pointing to this table, not any addresses, but this is pointing to this table, and this page table will point to one more page table, right, in the last level. Okay, that's this is this page assume this page this entry is pointing to this page table, and also assume there is a page table entry here. So if our program doesn't uses the address that is starting with this thing, we don't have to initialize a L1 page table for that, right? So assume this entry has a address. So this address is used by the address which is translated through this page table entries, this and this and this. So that page table, that page that are the tables we need, right? So these addresses are empty, and we don't create the next levels of page tables. We create these page tables only when needed. So even uh, if a program consumes very small memory, we don't initialize that pages. That address would be empty and it do not have. So this will be the L0 page table, right? And this finally, this whole address will point to oh, 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 the point to a physical frame in a memory, right? Oh, is it lost?
Okay, sir, yeah, got it. So, but so we have only one STATP register, right, for in the memory management unit?
So a CPU one at a time could point to only one page table, right? So there are one CPU can point it to only one page table at a time, since one CPU can run only one process at a time. So if a SATP register points to a particular page table, now we are in that process, right? So one process doesn't need two page tables. So the current process, the SATP will contain the page table for the running process.
Okay, okay, sir. Got it.
So any other things?
Could you show the slide where the swap diagram is shown?
Wow.
The swap diagram, the swap diagram with.
Subhendu, could you share that slide?
I wanted to know if swap is unique to a process as well.
Okay, let me share my screen.
So
Right.
Which slide can you tell? That Serene?
I think it's hardware.pdf.
Okay.
Okay, maybe the next one. Maybe it's processes.pdf. Sorry, memory. So yeah, here. So it was not mentioned in the lecture whether this swap space shown here 1, 2, 3, 4, 5, 6, that is also unique. That means separate swap spaces are created for each process, or it is one full entity.
So assume this. So there is this physical memory, right? So assume you have a 4 GB RAM. Okay. So there is an upper limit of the addresses that it can store, right? So each virtual address, every process has a virtual address space, and there is this physical address space, right? The physical address space consists of the number addresses in your physical RAM. Okay. So each virtual address will translate to an address in your physical RAM. So what if there is only a 4 GB RAM, and all the pages, which means the pages that are created for each processes will have a physical frame. So each page will have a physical frame mapped to it, right? So assume you have many processors running, and the physical frames, the memories that's needed to map the physical page frames is more than 4 GB. Then that addresses will be mapped to the swap space. And if that is not there, we will swap. So there is a separate mechanism for that also. If a page is present in this thing or not. So okay. So there will be this addresses, right? This swap and things. How? Yeah. So this is page table entry, right? So if a page is not present, if a physical address mapping is not present in the exact RAM, then it will create a swap page, right? So how do we see this? Okay, let me again share my screen, and oh, I was sharing my screen. Now is it visible?
Yes, it's visible.
Okay, so assume this is the physical RAM. Okay. So by address translation, so each process will have a virtual address space. Each process will have a virtual address space, and each the exact programs. So let's call this address space. This is address space 1. This is address space 2. Maybe let's do this. Oh, again. Sorry for that. So, okay, then I'll just draw this without using this thing. I just okay, we have this here. So we have an address space, right? So there is this physical address mapping will be there, right? So I assume the number of frames used by multiple processes. So every page is used by this process should be present in the physical memory mapped to some address. So what we are assuming is there is this additional thing. We assume our memory. So there is two separate things that are handling this. Oh, this is simple. Okay, so there is, we assume we also have this physical addresses. Okay, so there is another thing like, so our virtual address will assume if our virtual address is converted to address that present here, then what we see that that address is actually not present in the physical memory. So, but that is present in the swap space. So we load that. So you consider there is the physical address space. So this is the physical address space, not the actual RAM. And these are the virtual address spaces. So these two are abstract things. Actually, how that memory is managed. So actually, which frames are present in RAM and which are present in the swap are not things, right? So everything will have a physical address space and a physical a virtual address space. So if this address is not present here, what we do, so there will be a entry in the page table with a dirty bit so that it's present in the swap space. So we take that out and put it in some address here, right? Okay. In the exact memory, in the actual memory. So now this address page table entry, this virtual page table entry of this virtual address will map to this particular physical address in this thing. Okay, we change that. This will map to this physical addresses. So there are frames used for multiple things, right? Multiple processor. So everything will be in the swap space. So assume we are requesting with this page table, and it says that there is a dirty bit in that page table entry that says that this is not present in this particular location. So what we say, we just take that from the swap and put it here, something like that.
So that is done by the P bit, present bit. I think dirty bit.
So there is,
what it does is if it has changed while it was in swap, then it updates that value or something.
yeah, so that mechanism is there, right? So whether it's present there or not. So assume there is, okay, so assume, so more clearly, let's assume this. Okay. So assume there is two pages. So assume there is two pages which are mapped to exact same virtual address memory. So this that that is for this process P1, and this is a process P2. So these two pages are mapped to exact same physical address. Okay, so let's call this VA1. Here this VA1 and VA2 actually maps to this physical address, the same physical address. So when this process is running, so there will be if this is not present there, so this physical address is not present there, the present bit and the dirty bit will say that this is not present here, it may be present in the swap space. So we take that page and put it here. Okay, so we'll take the address of VA2, the page that contains the VA2, and place it in this PA1, a frame. We'll take that and put it here. So now then after this swapping, we'll read that address. So this happens automatically. Okay, so assume now if we have changed this, so now the process 1 tries to access this visual address. Now when we made here, put it here, the page table entry will be automatically updated, and this present bit and dirty bit will have the values saying that this is not present here. So when it tries to access after this access, it will take that value from here and put it there. Okay, this is how that happens. If you are trying to access a virtual address and that page is not present in the physical address, we'll take that from the swap. So if multiple processes are also running, we could do that, right? The page table entries are the one which has the details about whether that page is present here or not. So we'll whenever we change that, we take this out of the physical memory, we modify the present bit and the dirty bit.
Then one thing I wanted to know, how do you decide the size of the swap? If your RAM is 4 GB, then
So the page
what will be
size,
the...
so we don't transfer in addresses. Okay, we don't transfer these things in addresses, only we transfer the pages. We transfer the whole pages at a time. So you want to determine the size of the swap
of the entire swap. So if your RAM, the entire RAM size is 4 GB, what will be the entire swap size?
Okay, the entire swap size, that actually depends on how much of the things we need. It should be greater than the actual physical memory. So usually people keep it 2 times the physical memory, because if it goes more than physical 2 times, so it's basically actually depends on your need, right? How much of the things you need. So the need for swapping comes from the thing that the physical address cannot hold all the address of the things. If it can hold, it could do that. So we usually keep the 2 times the size of the physical memory.
So this example, it was clear when there are 2 processes.
Yeah.
But what if there are 3 or 4 processes? Then how does this present bit, dirty bit, swap and physical?
So each process has its own page tables, right? So there will be present bit for this virtual address VA1, VA2. So this is a different page table, and that is a different page table.
Okay, so suppose there is right now there's VA1, VA2, and suppose there is VA3 and VA4, which is also pointing to PA1. Then which value will be stored in the swap?
All the process, this address, this page here, this page present in the virtual address 2 will be also, every pages of the things will be in the swap. Okay,
Okay, so that means a swap is connected with process, or it is like it is identical to, it works somewhat similar to RAM.
yeah, it works somewhat similar to RAM. It doesn't know which process is using which memory, but it has pages. Okay, just like RAM, but here it is need not be ordered or something. Or maybe you can assume swap is kept here, and when you are trying to access, there should be something saying that this physical memory is present in that place of the swap, right? that kind of thing will be there. So there is some imaginary thing and it takes it from here and put it here again. It's basically so that your RAM is, so all the process could be accommodated in your RAM. Okay, you can see that as an extension of this RAM.
Okay.
If all the processes virtual address space, all the pages used by these processes can be accommodated in this RAM, there is no need for swap, right? Every pages will be every page will be allocated a frame and everything will remain in the same physical address space, in the address space, and there is no need of swapping. Only if we are having the number of processes which cannot be accommodated within this physical address space of the RAM, we'll add a swap space.
Okay.
Okay.
Then the other point is I was wondering about the maths behind deciding for this 3 levels of tables. How do you know that this 3 levels L3, L1 and L0, this is the most optimal, this thing which gives you the uh, best use of memory?
So you are asking why the level 3 levels of page tables is chosen.
So why
Why?
not 4 levels or why not 2 levels?
Okay, so as levels increase, the number of as levels increase, the number of the size decreases, right? The need for the total size of the page table decreases as the levels increase. So let's see this. Assume you have a page table virtual address space of maybe 4 GB, 4 GB, right? So it will be equal to 10 power 30, 32, 10 power 32. So there are this much, this is your address, okay? So assume each page has a size of 4 KB, which is equal to 10 power 12. Okay, then what is the size of this whole number of entries in the page table should be
10 power 20.
10 power 20. Okay, so now we need to have 10 power 20 items. Okay, so how much space we, so assume each page table entry is of 1 byte. Maybe let's assume for a simplicity, right? So it will be like 4 bytes in a, I think 16 bytes in a 64-bit operating system, and 8 bytes in a 64-bit operating system, and 4 bytes in a 32-bit operating system, right? The size of a page table entry, assume that's something like that. Okay. So now we need this much size of continuous address spaces, right? This much, this into 10 power 20 into, let's assume, so it's 4 bytes. 4 bytes. So 10 power 20 into 4 bytes is equal to 4 MB of continuous space, right? What is page table, multi-level page table? So we need a continuous things of 4 megabytes. But if you see, since we are organizing everything in the pages, this is the smallest amount of continuous thing we can guarantee. So each page will be a continuous block of memory, right? So this is the maximum amount of thing that we can guarantee within this thing. Oh. So we need a 4 MB of continuous memory to store this page table. In this case, if you are just storing in this much of thing, so there is this upper limit, right? But if we break down into multiple page levels, multiple page table entries in multiple levels, there will be same amount of there will be some amount of memory needed, but assume that need not be continuous, right? Because everything is splitted into this. So this page table can be in one page, and this can be in another page. Now we do not need a continuous 4 MB page, right? To address all the addresses in this 4 GB memory, we do not need a continuous 4 MB of page table. Okay.
Yes, got it. So it reduces the need for
A continuous block of allocate, yeah, that it reduces. And assume we have multiple processes, and each process's page table would have this much size, right? Since if this is the minimum number of thing that we are allocating, but in a case where multiple levels of page tables use, we need not create the page table for the other thing. So this a single page table can be, the size of the single page table can be reduced, and also we need not allocate page tables for the addresses. So this address will point to some page table, and this will point to page table, and assume our processor do not use addresses here, so we not create page tables for addresses that are available here. Okay, so that helps us reduce making the optimum usage of memory. And the fact that 3 is used is that uh, if you go and keep on going more and more levels, what will happen is that to trying and finding out reading, Lazim, you go here, go here, and to find one translation, you have to do multiple traversal, right? There is a traversal from each levels of page table.
The
So
walk
increase,
length will increase.
yeah, the walk length will increase, so that if you have multiple page table, so your system will slower, right? Get slower for each virtual address to physical address translation.
Hmm.
So it will be optimally chosen that the size of the page table should be the size of your uh, page. So your page table should, the lowest page table should have the size of your page. So what is the minimum size of page you have? And they kept that in 4 KB in that system. So by that you can find the size of a single page table. So doing that this much times, what is the highest address, the highest amount of address you need to make? So based on that, you can come up with this. So there is this S39. So we use a 39 bit virtual address space, right? In this RISC-V. So that
Yes, for
there is an
64 bit, you are using
there is an upper limit for that. I think we have discussed that in. So here is this. In this thing. So here. Yeah, here's that addressings. We have this 39-bit virtual addressing, right? So here 4 KB of page sizes. So each page will have 4 KBs. So using that, so this, what is the minimum size you need and what is the maximum number of pages that you need. So using this 32 thing, let me go here. This upper limit is given. I think the upper limit of this is 512 GB. The using 39, like, yeah, 2 power 39 means, yeah, it's 512 GB, right? 2 power 39 will be equal to 5 power 512 GB, and that 512 GB is the highest memory that this address space can use. Okay, so there is this 4-level thing which is SV48. So that should be equal to 256 TB actually. Yeah, 256 TB this can handle. 2 power 48 is the virtual address space. What is the highest address space that you can handle that case? We have these levels of addressing schemes, but in XV6 we chose this one. This is based on the RISC-V architecture. Okay.
Okay, got it.
So if you are not planning to use very large memory intensive application or a system, we need not design a virtual addressing space that consisting of 4 levels of traversing, right? So that would usually decrease the performance of the system.
Okay,
So
this
you could,
4 level of traversing is for 48.
yeah.
Okay.
So XV6 is designed to operate in this mode, 32-bit virtual addressing mode, with 4 KB of pages. So in this, you can also have different page sizes like mega pages. There is something called mega pages and giga pages. So if you need a continuous block of this could also support this KB of pages and also support 2 MB and 1 GB of pages by using intermediate level page translation. So you need not go 3 levels, you just go 2 level and it will translate to a physical address. So that kind of thing also can coexist in the same physical page table address scheme. This is an address scheme if you call it. Okay.
Okay, got it.
Any other doubts?
So regarding in week 4 about forking,
Okay.
so there was one concept of copy on write,
Yeah.
where when the variable is changed both in child and parent process, it creates a copy of the page frame. So my doubt is just for just one variable change, do we copy the entire page frame? Won't it
Yeah.
be
Yeah.
inefficient?
Yeah. Yeah. We copy that page. So it will be inefficient. So if you want to have two processor working on the same, like if you just want, so assume, so the variables that are used are only a small number of things, but the shared libraries like the functions defined for printf and these kind of things will be there, right? These could contribute more pages than the pages that uh, have one variable. So for one variable that is changing, we are copying a page. So if you want to make it efficient, like if you want to have one more variable that is doing something, you could have done it in a same process itself, right? Why do you need to create a new process for that? This is just to demonstrate we have this code. So if you want to have a program that computes two different things, you can just do it in a same program, right?
I was just thinking in terms of operating system. Why does operating system just copies the whole page frame? Why doesn't it just create a only? Why doesn't it just use another address, another virtual address?
So if there is this concept of page swapping and these things were right there, right? If assume if you are for every addresses you have to swap many things, then this swapping overhead may take more time than actually having these values. That's why we keep things in pages, so that we only need to do minimum number of swappings.
So swapping in the sense.
The page swapping. So there is this memory, physical memory, and the swap phase or space are there, right?
Okay,
So
okay, yeah.
copying a whole page is easier than copying multiple different addresses. The overhead will be high. That's why we create memory in pages. If you want to create for each address, then there should be another address, right? Then we cannot implement things such as this address space schemes and using that.
Okay, sir. Okay.
So any other doubt?
Also, so one thing in the lecture, the zombie process was not clearly explained. I mean,
A,
in the
a zombie process is a process which is terminated. So like there will be a kill system call or something like that where we'll write a system call or this program should have been exited. The exit system call actually makes the uh, process a zombie process. If you could see, let's see this. So there is this process. Dot. Okay, it is here. It is in the proc.c. There is the exit system call, right? There is this exit system.
basically every process becomes a zombie process during exit, right?
Yeah, you could see that this exit system call makes the state of a process zombie. So
Yeah,
whenever
yeah.
a process exists, it becomes a zombie.
Actually, in the lectures, made a statement before that when the parent process gets terminated before the child process, then it becomes zombie. So
No,
that's
no,
why.
it's an orphan. If a parent process exits before a, that is called an orphan. It's not called a zombie. So there is this
Yes,
orphan
but in the
process and
lecture
zombie.
it was there was a mistake there, like in 8 minutes something.
Yes, in the lecture he had mentioned that for both zombie and orphan process that he had mentioned the same thing.
Same thing.
Yeah.
So I'm not sure it's there. So it's in the lecture number.
Either 3 or 4.
It's week 4,
Number
right?
2, I think. Number 2.
This one.
Yeah, okay.
About 8 minutes something, I think.
Here he. If a process terminates, it becomes a zombie, right? And about orphan process, when a parent process terminates, it before its child, it's an orphan. So there is this difference. If a parent terminates, it becomes an orphan. If the process terminates, so here this process is terminating, right? So this will become a zombie and this will become an orphan.
So regarding that copying of the resources from the parent and orphan. So what will happen if the parent terminates?
So if the parent terminates, what happens is when this is exiting, so let's see this exec system call again. So I am exiting, right? So there is this thing called reparent in exit system call. So what it says that all of the children of the current processes, when I exit, I gave my children to the init. So if you see this function, what it does is it takes all the children. So it goes through the process control block of the different processes. And if this is checking just what is checking, so is this visible, the code?
It's visible.
Okay. So what this reparent does, so this is in the exit system call only. When a process exit, it says that we are finding the children of this. From all the processor, we are finding which processes has this current processes, the exiting process as a parent. So actually this P is a child of PP. No, this PP is the child of P, the current process. So PP's parent is the current process. So PP is the child. So what we are saying, we are making PP's parent as the init process. So whenever a program exit, it gives all its children to the init process. So that's what is represented in this diagram. Whenever process exits, this process gives its child to the init, and this becomes a zombie, and we call it an orphan. There is no state such as orphan. We just call this kind of processes which are given back as orphans. But zombie is a process state.
So will any return value will pass to that new parent?
Which parent?
The new assigned parent for the child.
The new parent is the first process. This is the init process. The first process, if you see the lecture 4.3, you will see how the first process is loaded. This is called as the init process. All the other processes are forked from the init process. So there is one process, init process, that is running through all the other processes, and if this process is executes, this will go to the init process, the first process which is loaded into the user space. Okay, so this is kind of this running this in background. Okay.
Okay, sir. Okay.
We also call this kind of process daemons. So it will be mentioned here. These are called as intentional orphans. We intentionally terminate our parent to go back, make it the thing. So these are unintentional orphans, which means the parent is terminated due to an error or something. Okay. So this comes from the exit system call. The reparent is called in the exit system call. Is that? Yeah. Here the exit system call. Here it's in the exit system call. When a process exits, we just check this. So if you just go through this code, you can see multiple things done here. If we check, first we are checking whether the process is the init process or not, which means we should not exit from the init process. It should be always keep running. Okay. So if we are trying to this thing, we are panicking and the whole thing crashes. So we should not exit from the init process. So if that crashes, everything will crash. That kind of thing. And the other thing, what's this? Yeah. This is the thing for doing the closing and open all the open files. So it goes through the open files of this particular process and closes all those files. And this, yeah, so they are putting some lock and things and doing this reparenting thing. So there is this original parent is the process of P. Okay, so there is this locking mechanism which is not covered yet. And there is this reparent function. What this does, this reparent takes all the childrens of the process P and give it as the childrens of process, the init process. And there is this wake up call, which means if the parent of this process, these are to handle the children of this process, and this is to handle the parent of this process. So like the parent will be waiting for the using a wait system call. So this wake up is used to set that to, okay, where is this? Yeah, this is to, so parent will be in a sleeping state, we'll change it into the runnable state. So when a process exits, if its parent is waiting, sleeping, then we will wake it up by making it a runnable process. Okay, and then you can see how this, so we do things, handle the children's and handle the parent, and then after that we'll set exit status. It will come from the exit system call. The status will come from the exit system call, and we set the state of the current process to the zombie.
Okay, then how will we pass the exit status value to the parent?
Passing the exit status to the parent.
Yes, whenever the process exit, it passes the value to the parent, right?
No, we just say that this is a zombie process. Now this process becomes a zombie, and we set the exit status in that process of this process to here. So this P, where is this P? This P is present in the process control block. So there are the 64 process running in the XVSys operating system. If you see this proc structure is there. If you see this proc structure will hold all the processes that are running in the current thing. Okay. So when this is become runnable, okay, let me show that. So in the exit system call, so there is this sys exit is there, right? So there is this sys exit thing is there. So that is defined in another thing. I'll just do. So this is just the exit function, and the system call for that is defined in the sysproc. And if you see, this is what the exit system call will look like. Where is that? Do we here it is, right? So this is how the status is written. So the exit system call, we will have an address. There will be an integer. That return address will be passed through this exit system call. So here we call that, right? So when this process becomes a zombie, what happens is we are setting the proc structure to that, right? So the parent have to claim the things. So this process still exists in the process control block. It will not be termed as unused. Only new processes are created where when there is an unused process in the process structure. So the zombie process, so we set that exit stated in the that thing, right? We set that here in the this X status. So this proc structure is present in the kernel. So any process, the kernel can see when that is there. And there is this wait system call. If you see wait system call, what it does, it checks whether the what this wait system call does. it checks whether the child, so this child is, these are the child of the process. If any process is a zombie process, then it checks that what is these things are there. Okay, and this address is reading the X state of that process, exit status. It will take that exit status and do a copy out. The kernel is passing the exit status. So this copy out, what it does is, so now this exit status is present in the kernel. The proc structure is present in the kernel, right? So it takes that, and this address is the address that, okay, this address, where is this coming from? Yeah, of the wait system call. So in the wait system call, we pass an address. If you see in the wait system call, we pass an address from the user space. So that address, we'll write the value of the exit status.
Okay, yeah.
But this address is not the kernel space address, right? It's the process user space address. So in kernel, we have to use the copyOut function and use the page table of the process and this address. So this address is the address from that page table, right? Not the kernel's page table. So that's why we are copying that exit status to that address of the parent. So the parent will pass the address in which it needs the exit status to the system call, and this function will run, right, in the parent. So it is just an infinite loop until it finds a child which is a zombie. The wait will just it's just a for loop that checks whether any of the child is a zombie or not, which means the child has exited.
Okay, so yeah, got it.
What does wait return? When you call wait, what does it return?
So this just returns the process PID.
Okay.
You could see. So this, in this case, if it is address is not equal to 0 and this is less than thing, which means it worked. It kind of like, I think this is the wait failed. This is the condition for failing for wait. And if it passed, it just frees the process structure, which means now we found one that is zombie, right? And this zombie, when called free proc, will change to unused, and we return the process PID, which means the now the exited process is this child. We have to know which child exited, right? From the parent has to know which child is exited. So we'll return there will be multiple child, but when the wait system call exit, it just returns after one child which is exited. Okay, so we want to know what child is just now returned, which is the child that returned just now, so that we return the PID. Okay, so this free proc, if you could see, that will use the free the page from pages used by that thing, and the free proc page, you can see the state will be set to unused. So this thing, after the wait system call, freeze the thing. So after the exit system call and the wait system call, so exit system call of the child and the wait system till the wait system call of the parent, the exited process will be in a zombie state. Okay. Okay. So
So
if
can you please also explain the involuntary termination? How the code works for that?
involuntary termination means using a kill statement, a kill
Yeah, yeah.
statement, which means involuntary. So that will be present also in this proc.c thing. So his kill is there, the kill is here, right? You could see same kind of thing has happened. If it's killed, it will be changed to So there is this process PID. Now what happens? That process, we say that it is killed, and okay. So what is this?
There were some signals, right? The SIGTERM and SIGINT, something like that.
Okay, so this is the SIG term. There is the skill statement, use a SIG term to do that. There is interrupt and other kind of things. So let me try this. Okay, so if a process is killed, we state if it is sleeping, we change that to, if a sleeping process is killed, we change that to runnable. And I think this thing is handled if a process is killed. This is a part of a scheduler, I think. So we go to main. So everything branches out from the main. If you see the scheduler, yeah. Okay, so let's see. Let me search this. So okay, there is this killed. Let's see this. Is it this two killed? So 427. Yeah, what is this? Yeah, wait. If no, so in that kill system call, we are just making that to killed. Okay. If this is killed in this console, if something is killed, we are doing this. Okay.
10 minutes, sir.
So I think I am not sure how that thing is handled. So waiting, the voluntary return is handled by this wait system call. So wait system call would reallocate that thing as we saw that in the proc file. So wait turns that
Is
zombie
that a
to
part
this.
of interrupt or something?
So this makes this zombie. So usually when we voluntarily exit, it makes it a zombie, and the wait system call does this thing. And when it's killed, it should be something related to this kill system call. Let me go through it again. Yeah. we set it to this thing.
So if you execute no HUP, then that will kill the parent process and make it a daemon kind of thing.
Yeah, sorry, what? Execute what?
If you execute no HUP,
So that is not actually, that no hub is not actually present in this thing, I think. The XV6, it's a general things to create daemon process in Linux. There is a thing called no. Yeah, there is this utility there. Okay, not present in x86 actually. That no hub. This helps us to create a process.
daemon.
Yeah, you could see run a command without interrupting it, so it will be running forever.
And I think just now, while you were scrolling through the code, that init code array of binary, that binary array was visible.
Which one? Yeah, that is just this thing. If you go to the main, there will be this. So this one, right?
Yes. So what is the use of initcode.s if initcode binary is here?
Okay, so this is the binary. So we are.
There is a assembly file initcode.s.
So I think that compiled will give you this binary, and they have copied it here. I think so. So that assembly code is not.
That is in the user space.
Yeah. So this is a thing. Yeah, they have given this command to compile that. I think this is the command after compiling the init code.s. Where is that? Oh,
It will be in the user directory.
okay. Yeah. I think this whole thing was compiled and it was put into put it. I am not sure about this command. If you could see, there is a command given, right? I'm not sure about this, but I think that could be the thing. There is this command od. I'm not sure what od does. Let's quickly search it. Okay, yeah, it just displays. It's just dump the object in the binary form. If you could see, so which means if I run this command on the init code, so let me download this file, or where is that? Initcode.s. It's just a hexadecimal representation. If you see, it's all hexadecimal representations, right? They dumped it and put it here. Where is that? Initcode.s. Okay.
Init code will only be available after using make command.
Oh yeah. After make, this will be created. Oh, which means they have written this thing and they turn back it into that thing. So let's copy this and try this out. Let's see what it where it takes us. Oh, let me. Okay, we'll try this. We'll create a new file. I can't create a file.
So you look offline, I guess.
Oh, should I refresh this? Okay, so just a minute. Yeah, we got the file. So just a minute. Okay, so paste this. State. Set command that comes from this data. So this init code is generated from make command. Looks like there is much of. So where is this? Is there any file init? Programs and calls. That is this thing. Exec init is called by this using the exec system call. This is the first thing. Okay, so we are setting this thing. I think this is after removing this, all these things maybe it should look like that. These instructions. So this is what uses the exec system call to make this thing. So maybe if we could print out that, or we just take this and print it out. Let's see what's there in this. For the reverse, we'll start from the init code. So it's just a string, right? If you see, this is just a string in C, character array. We just try to print it. Let's try. Sure, it's not there. Let's check. See what's nothing is printed up. it's in a compiled form or this thing. Let's look at this. So yeah, this is how the init process is called. Yeah, this is init code. First process return assembly. Okay. So where this user init code is used here, it's just to where is that used? Yeah, while creating the init process, the first process we put that here. So how this is created, we say that this is how the now is it clear?
Yes, sir. Now it's clear.
Yes, it's clear.
So I think this should be the object of that init code which is present here. I think this also has some so it's just not printed correct way. Maybe it should be okay. I'll check this and we do the next session.
Can you just delete the other main file? Maybe that
Sorry.
in the replet. In the replet, there's one more main file.
That just is compiled from this file. That main file is compiled from this main file. Yeah, I think these are actually unprintable characters. So nothing lies between the ASCII thing. Maybe when you compile this init code, not sure how to compile that. How we compile the assembly code. I think it should be compile that assembly code. It will try if it has something like that. We need a yeah, that is compiled from a different tool. The RISC assembly is compiled using a different tool. If they compile that init code using that, and that init code when compiled will create it will give out this code. So that is a source code, right? So this init code.s is a source code. Oh, okay. So let me do this. Real quick. Yeah, here we have. Yeah. This is 13 code, right? This is 13. So that is compiled form. When you run that compile, it will come. So this is the source file. It code as this is source file, and that thing here goes. Yeah, you could see that init code that is compiled and it's coming here. So it's present in the user directory. Here. Yeah. It's 1705. Same thing, right? After compiling, it would be this value. Yeah, 17050000130505 and this thing. That is the compiled init codes byte view. Okay, so that's assembly code. Init code.s is got compiled into init code. After you compile, it will be presented there, not in the source file. After you compile the kernel, make qmove, this will be present. This init code binary file. And if you see, these are the contents of that binary file. Okay. They compiled it beforehand and put it in the kernel file, the first init process.
Got it. Thanks.
So anything else?
No, sir, that's it for today.
Thanks, Stephen. Thanks, Eric. I think we can wind up the session, right? Thanks for joining.
Thanks.